Hello, I'm Norman Wildberger. Today we're going to carry on with our course in linear algebra, and we're going to look at change of coordinates again, and we're going to systematize what we've done earlier. We're going to introduce various applications or interpretations having to do with systems of equations, and we're going to look at a matrix formulation for those manipulations, culminating in a very important theorem on determinants. So let's start off by redoing or reminding you of a very important calculation that takes this relation between two pairs of variables and inverts it. So we have y1 and y2 expressed as linear combinations of x1 and x2. And what we want to do is we want to invert that. We want to express x1 and x2 in terms of y1 and y2. And let me remind you how we did that. We did it in two separate steps. So in one step, we take the first equation multiplied by d and the second equation multiplied by b. We do that so that there's a common term, bd times x2, so when we take the difference between these two equations, that term drops out. Taking the difference gives us this equals ad minus bc times x1. And so we can solve for x1 in terms of y1 and y2, and this is what we get. d over delta times y1 minus b over delta times y2, where delta is this determinant type expression that we've seen already a number of times. It's an area kind of expression, AD minus BC. On the other hand, to get x2, we take the same pair of equations, multiply this one by c, this one by a, take the difference, then solve for x2 to get minus c over delta y1 plus a over delta y2. So let me remark on the symmetry between these two things. Both of them are expressing one pair of variables as linear combinations of the other pair. And to go from this one to this one, if we take out that common delta in the denominator, then the other coefficients are obtained by interchanging the a and the d and multiplying b and c by minus 1. So that's relatively easy to remember, and it's important that you remember that. Let's have a look at how it looks in some applications. In our first example, we have y1 equals 3x1 plus 2x2, and y2 equals minus x1 plus 5x2. The first thing that we do is we calculate the delta constant, which is 3 times 5 minus 2 times minus 2. That's 17. That's the denominator that appears in each one of these coefficients. And otherwise the coefficients are obtained by interchanging these two diagonal ones, the 5 and the 3, and multiplying these off diagonal ones by minus 1. So we get 5/17 y1 minus 2/17 of y2, and x2 being 1/17 of y1 plus 3/17 of y2. In our second example, we have, instead of y's and x's, we have t's and u's. We have to be prepared to be flexible and to use different coordinates or variables because many applications have different notation. So here we have t1 and t2 expressed in terms of u1 and u2. In terms of those equations, t1 is 4u1 minus 3u2, and t2 is 3u1 minus 2u2. In this case, the determinant is 4 times minus 2, which is minus 8, minus 3 times 3. So that's minus 8 plus 9, which is 1. That's very nice because then the denominator is 1 in each case, and we get a relatively simple solution. We get the minus 2 and the 4 interchanged, the diagonal terms. The off-diagonal terms multiplied by minus 1 so become 3 and minus 3. And so there are u1 and u2 in terms of t1 and t2. And for our third example, we have r1 and r2 expressed in terms of s1 and s2. R1 is 2s1 plus 3s2, and R2 is 4s1 plus 6s2. The determinant in this case is 2 times 6 minus 3 times 4. That's equal to 0. Well, determinant 0, that corresponds to an area of 0. That's a special case. And our method fails in that case because the denominator would be 0, which is not allowed. So our method fails and we do not know how to invert and find S1 and S2 in terms of R1 and R2. Now let's have a look at some geometrical interpretation of what's going on here that will help us interpret what's going on in this latter case. The fundamental problem of a change of coordinates is related to a more specialized problem of solving a system of linear equations. So to illustrate that, let's have a look at this system of linear equations. We have two variables, x and y, and we know that x plus 2y is 6 and x minus y equals 1. Now, each one of these equations can, in a traditional high school way, be identified with a line in two-dimensional space. You're probably used to writing a line in terms of y equals mx plus b, but this kind of equation also represents a line. And to find out what kind of line it is, here's the usual x and y coordinate system. And if we set x equal to 0 in this first equation, then y is equal to 3. That's telling us that the point 0, 3, this one up here, is a point on this line. And if we set y equal to 0, then we get x equal to 6, telling us that the point 6, 0 is also on that line. So 2 points determine a line, so that first equation represents that line right there. The second equation, x minus y equals 1, has when x equals 0, y is equal to minus 1, that's that point. And when y is equal to 0, x equals 1, which is that point. So that's that line there. And when we have both equations, what we're interested in is a point which is on both lines. Geometrically, that's the intersection of those two lines. So this is a very common and important problem, how to find where two lines meet. Well, we can recognize that this is a special case of the more general thing that we've been talking about. This is a special case of this more general equation where we have x plus 2y equals, say, r, and x minus y equals t, and we want to solve for x and y in terms of r and t. That's exactly the kind of problem that we've been looking at. Well, what is the determinant in this case? It's 1 times minus 1 minus 2 times 1. So that's minus 3. And so our formula is that x equals, let's take the common determinant out, 1 over minus 3. And then the 1 and the minus 1, the diagonal terms here, they interchange place. So we get a minus r and a t. And the 2 and the 1 here get multiplied by minus 1. So we get minus r minus 2t, and minus r plus t are the values for x and y. And now if we replace r and t with these particular values 6 and 1, put 6 in here and 1 in there, then we get minus 6 minus 2, that's minus 8, with a minus sign here, is 8/3. And here we get minus 6 plus 1, that's minus 5, with the minus 3 there, is 5/3. Telling us that the point of intersection that we're looking for is the point with x coordinate 8/3 and y coordinate 5/3. And to check that that's the right answer, we should go back to the original equations and check that these values actually satisfy both equations. Let's do that. If we take x plus 2y, what do we get? We get 8 plus 10/3, that's 18/3, that is indeed 6. And if we take x minus y, 8/3 minus 5/3, that's 3/3, that is indeed 1. Now this solution allows us to see a more general pattern here. We could have done not just 6 and 1, but any values here. This same formula would have worked. Now what happens to the lines if we change the 6 and the 1 to other values? Well, what happens is that the lines simply move in a way that's parallel to the original lines. So if we change the 6 to something else, this line changes something like that. And if we change the 1 to something else, then this line changes to something else. So this more general solution is really capturing a whole family of problems all at once. Now let's have a look at another example a system of equations, 2x plus y equals 4 and 4x plus 2y equals 3, where something quite different happens. In this case, the line 2x plus y equals 4 goes through the point 2, 0, and it also goes to the point 0, 4, so there it is right there. And this line here, we can find out where it goes through by setting x equal to 0, giving y equals 3 halves, up there. And we set y equal to 0, giving x equals 3 quarters, which is right there. And that line, therefore, is this one. And if you look at these two lines, they are parallel. So if we're looking for a point which lies on both of those lines, then we're going to have a hard time, because those two lines are parallel, they do not meet, telling us that there's actually no point, x and y, which lies on both lines. So trying to solve those two equations at the same time is an impossibility. Now if we went through our method, what would happen? Well, we calculate the determinant. 2 times 2 minus 1 times 4, that's 0. And that determinant being 0 is telling us geometrically that the two lines are parallel. The determinant being 0 is telling us that the two lines are parallel. Another way of seeing that from the original equations is that the left-hand side, the 2x plus y here, and the 4x plus 2y, they are multiples of each other. But if you take this thing here and you multiply by 2, you get that. It's another way of seeing that you're going to have some problems in solving that system of equations. One of the interesting features about linear algebra is that a particular abstract problem can often be interpreted in more than one way. Or to put it another way, we could often end up solving two quite different looking problems at the same time. The problem that we've just been looking at, x plus 2y equals 6 and x minus y equals 1, we've already given a geometrical interpretation in terms of the intersection of two lines. But this problem also has a quite different interpretation, which is equally important. To see that, let's rewrite this system in a vector format. So what we do is we look at the coefficient of x, and there's a 1 and 1 here. We put them together in this vector form. So 1, 1 represents the two coefficients here. 2 minus 1 represents the coefficients of y, and 6, 1, that vector is the right-hand side. So this one vector equation contains exactly the same amount of information as these two linear equations. And when we think of it this way, as written as x times the vector a plus y times the vector b equals the vector c, then we have a situation where we're looking for some multiple of a plus some multiple of b equals some given vector c. And the geometrical interpretation of that can be illustrated here. We choose, first of all, some reference affine frame given by two vectors e1 and e2. And the choice of that affine frame is completely arbitrary. In terms of that choice, we can interpret these vectors as actual vectors in the affine plane. So this vector a, which we're thinking of as being the vector 1, 1, would be this vector here. 1 over in the e1 direction, 1 over in the e2 direction. So that's the vector a. The vector b, this one, 2 minus 1, that would be 2 over in the e1 direction and minus 1 in the e2 direction. That's the vector b right there. And I put a and b together so that their tails are together, so that it's easier to see what happens when we take combinations of them. The vector on the right-hand side, the vector 6, 1, is 1, 2, 3, 4, 5, 6, 1. It's that vector c there. So geometrically, what this equation is asking for is it's asking us to write c as a combination of a and b, as some multiple of a plus some multiple of b. And geometrically, we can see what that means is we have to create a parallelogram which has one corner there, whose sides are parallel to a and b. There's the parallelogram right there. This expresses c as that multiple of a plus that multiple of b. Now we've already solved this problem. We've seen that the solution is 8/3 and 5/3. Now we can interpret what that means in this vector formulation. It's saying that we need to take 8/3 of this vector A. That vector there is 8/3 of A, so almost 3 times A. And this vector here is 5/3 of B, almost 2 times B. And those are the multiples required so that this component plus this component add up to C. So it's quite a different interpretation of the same system of linear equations. And this kind of flexibility will be important for us to carry through this course. The idea that a particular system or equation that we write down in vector form might have different interpretations. To further illustrate that point, here's that second example that we've already worked through. The system 2x plus y equals 4 and 4x plus 2y equals 3. If we rewrite that as a single vector equation, it would be 2, 4, the vector 2, 4 times x plus y times the vector 1, 2 equals the vector 4, 3. Or x times the vector A plus y times the vector B equals this vector C. And geometrically, once we've chosen an E1 and an E2 rather arbitrarily, we can interpret this by writing down what these vectors look like. There's the vector C. It's given by 4, 3. So in this case, 1, 2, 3, 4, and 3 over. That vector there, same as that vector there. And the vector A is the vector 2, 4. That would be 2 over and 4 over. That's that vector, or that one there. And the vector B, vector 1, 2, will be 1 over and 2 this way. And what we've seen here is that the vector A and the vector B are exactly multiples of each other. In fact, the vector B is exactly half of A. And we can see geometrically why this is not going to have a solution. Because if we take any multiple of A and we add any multiple of B, we're still going to have a vector which is in this direction. We're never going to be able to combine those two vectors to get a vector that's in this direction. So it's another interpretation of why this system does not have a solution. It's quite different from the interpretation of having two parallel lines. Now let's have another look at change of coordinates and introduce a third set of variables. Many courses of linear algebra focus on systems of linear equations as being the essential issue. For me, I rather think that it's change of coordinates which is the heart of the subject. And the systems of linear equations is just an important special case of that more general idea. So let's return to this change of coordinates business where we have y1 and y2 expressed as a linear relation involving variables x1 and x2. This particular choice has a delta of 3 times 2 minus 1 times minus 1, the delta of 7. And now let's introduce another set of variables, say z1, z2. And we'll suppose that z1 and z2 are known as linear combinations of the y variables. So that z1 is y1 plus 2y2, and z2 is minus y1 plus y2. This change of variables also has a delta function associated to it. It's 1 times 1 minus 2 times minus 1. That's 3. And now a very natural and important question is, how can we express z1 and z2 in terms of the original variables x1 and x2? Well, it's not hard to see how to do that because we can see that z1 and z2 are combinations of y's, and the y's are themselves combinations of x's, so it's simply a two-stage process of substituting these values into here. So let's see what happens when we do that. So here's z1 and z2. We're taking y1 plus 2y2, so we're just substituting these two values in for y1 and y2 into here. And z2 is minus y1 plus y2. There's y1, there's minus y1 plus y2. And now we just expand this out. There's 3x1 there plus 2x1. There's a total of 5x1. There's minus x2 plus 4x2, a total of 3x2. Here there's minus 3x1 plus x1. That's minus 2x1. And plus x2 plus 2x2 gives 3x2. And this is now the desired relation between the z variables and the x variables. Notice that it's also a linear relation. So we've gone from one linear relation here and another linear relation here to a third linear relation between the x's and the z's. Also note that the delta of this system is 5 times 3 minus 3 times minus 2. That's 15 plus 6. That's 21. And what's the relationship between 21 and 7 and 3? Well, I think you all know what that is. And that's going to be a very general rule, that when we combine changes of coordinates, then determinants multiply. A very important fact. There's an analog to what we just did in the one-dimensional case, which is vastly simpler, but it's also important to keep it in mind. Suppose we just have three variables x, y, and z, and we know that y is 3 times x, and we know that z is 5 times y, and we want to know what's the relationship between z and x. Well, it's very simple. Z is 5 times y, and y is 3 times x, so we just plug this into there, and we get z equals 15x. What we've done here is just a fancier version, a two-dimensional version of this simple one-dimensional business. So let's try to understand the example that we just did by generalizing it, by replacing the particular numbers that were involved with letters. This is the usual way for us to gain understanding, a bigger picture of what is actually going on. So we'll still have y1 and y2 as linear combinations of x1 and x2, but now the coefficients are our friends a, b, c, and d. Arbitrary numbers. And we'll have z1 and z2 as functions of y1 and y2, and let's introduce some other coefficients. Let's say e, f, g, and h. So the natural question now is, given this relation between the x's and the y's, and this relation between the y's and the z's, what is the relation between the x's and the z's? How do we combine these two changes of coordinates to get a bigger change of coordinate? Well, we do exactly the same thing that we've already done, except we have to work with these letters. So here are z1 and z2. We're just basically going to repeat this, e times y1 plus f times y2, where we're replacing the y1 with this expression and replacing the y2 with this expression. And z2 is g times y1 plus h times y2, again replacing there g y1 plus h y2. And we now rewrite this, just expanding and putting all the x1s together and all the x2s together. How many x1s are there? There's e times a plus f times c. And how many x2s are there? There's e times b plus f times d. In the second line, how many x1s are there? There's g times a plus h times c. And how many x2? There are g times b plus h times d. So this perhaps intimidating looking formula tells us how to combine this change of variables with this change of variables to get the change of variables between the x's and the z's. It's an important formula, but I'm not going to ask you to memorize it exactly. What we're going to do is establish a bookkeeping kind of system that allows us to keep track of this kind of thing more efficiently. We're heading towards introducing matrices to encode the coefficients that are appearing in these changes of variables. All right, so we're going to establish some abstract notation that makes it a lot easier to keep track of various things. So we're going to introduce the idea of vectors and matrices in a particular form. Well, a vector is something that we've been talking already about. We're going to eventually call this a column vector because it could also be a row vector. So a column vector is just a pair of numbers, one on top of the other. And a matrix now is an array of, in this case, 4 numbers, say 3, 4, minus 1, 5. And we're going to agree on how to multiply a matrix by a vector. This is the rule that we're going to use, and it's exactly the rule that comes to us from that change of coordinates formula. So the rule is that if we have a matrix like this and a vector like this with the matrix on the left and the vector on the right, then the product of these two things is going to be another vector. And to get that other vector, we're going to do the following. The top entry is obtained by taking 3 times 1 plus 4 times 2. So we're going to go over that first row and multiply the terms one by the column elements in the vector and add them up. 3 times 1 plus 4 times 2. That's 3 plus 8, that's 11. And the second entry here is obtained by taking the second row of the matrix and also multiplying it by this column. Namely, minus 1 times 1 plus 5 times 2. That's minus 1 plus 10, that's 9. Here's the general formulation, which maybe is a little bit easier to see. We have a matrix A, B, C, D on the left, a column vector x, y on the right, and we agree that this product is A times x plus B times y, that's the first entry, and C times x plus D times y, that's the second entry. So a matrix times a vector or column vector is another column vector. So this notation helps us simply to rewrite something that we've written many times before. It allows us to rewrite a pair of equations like this into a single relation involving a matrix times a vector. Because what's happening here on the right is exactly the product of this matrix times this vector. The top entry is ax1 plus bx2. The second entry is cx1 plus dx2. So saying that y1 is this and y2 is this is exactly the same as saying that this vector is equal to the product of this matrix and this vector. Similarly, if we have a second change of variables going from y1, y2 to z1, z2 like we did before, then we can rewrite that in terms of this new notation by saying that z1, z2 is the matrix EFGH, matrix of coefficients here, times the vector y1, y2. So this is a kind of a shorthand. It's a little bit more efficient than this kind of thing because we don't have to repeat the variables all the time. In the 2 by 2 case, there's really not that much difference, but if there's many more variables, then the difference between these two things becomes quite noticeable. All right, now let's think about combining these two changes of variables like we did earlier. Let's take z1, z2 from here. This is equal to EFGH times y1, y2. And y1, y2 is itself, from this equation, ABCD times x1, x2. So if we write it this way, we see that we have three things multiplying. And we made a computation earlier that tells us how to combine these two change of variables into a single more complicated change of variable between the z's and the x's. And these were the coefficients that we determined earlier. Right. So we know that the result of this double change of variables should be that z1, z2 should be this matrix times this vector. Now if we stare at this equation, we see that it compels us to think that the product of these two matrices should really be this matrix. In other words, for this notation to be kind of consistent and to make sense, we had better define the product of this matrix and this matrix to be this, in order that this and this being the same makes sense. So the product of two matrices is forced upon us by our earlier understanding of changes of variables. It's not something that we're going to make up arbitrarily. We are going to define the product of this matrix times this matrix to be this matrix here. But we prefer to write it in a little bit more efficient or concise way. The discussion that we've been having so far motivates our definition of a kind of arithmetic with matrices and vectors. It turns out that this arithmetic that we're going to study is in some sense independent of the applications that we have in mind. Or to put it another way, that this arithmetic applies to a number of different applications which are sometimes quite different looking. It makes sense, therefore, to think about introducing this notation and this arithmetic completely independently of any application. And that's what I'm going to do now. I'm going to almost start from the beginning. And in some courses in linear algebra, this is actually where we start. So you could imagine not having listened to any of my prior videos, and I'm now going to start by telling you what vectors and matrices are, or what column vectors and matrices are, and how their arithmetic is defined. Let's start by defining a column vector. A column vector is just a pair of numbers in a roundish bracket. So there's two examples of column vectors. And I'll say column vector to distinguish the kind of row vector that we are also going to be talking about later on. And here are two very particular examples of column vectors called A and B. There are two kinds of operations we can do with column vectors. One of them is we can multiply a column vector by a number. That's called scalar multiplication. So lambda times x, that x there, is defined to be the column vector lambda x1, lambda x2. In other words, we just multiply each entry by lambda. So for example, 5a is 10, 15. Minus b, just multiply each of the entries by minus 1, 1 minus 4. And the other operations that we can do are vector addition or subtraction. So x plus y is defined to be x1 plus y1, x2 plus y2. And the difference, same thing with negative signs there. So a plus b, the sum of these two column vectors is 2 plus minus 1 is 1, 3 plus 4 is 7. We just add component-wise. And the difference, a minus b, is 2 minus minus 1, that's 3. 3 minus 4 is minus 1. So this approach is independent of any geometric interpretation. We don't have to have a mental image of a vector as being a directed line segment. It's a purely algebraic thing that is independent of any geometrical attachment. The operations of scalar multiplication and addition and subtraction of vectors are subject to some pretty obvious laws. And we'll write them down just for reference. These laws are pretty obvious. The first is that x plus y equals y plus x, the commutative law. That if you have three vectors, x plus y plus z, you can combine the x plus y by addition and then add z. You're going to get the same thing that you get if you take x plus the sum of y and z. It's associative law. There's a special vector called the zero vector, whose components are 0, 0, which has the property that x plus 0 is x for any vector. There's an associative law in terms of scalar multiplication. If we multiply by mu and then by lambda, that's the same as multiplying by lambda mu. There are two distributive laws. Lambda times x plus y is lambda x plus lambda y. And if we take two scalars, lambda plus mu times x, that's the same as lambda x plus mu x. And finally, there's a kind of a negative law that tells us that if we take a vector x and we subtract it, which is the same as adding minus 1 times x, then we're going to get the zero vector. Of course, these column vectors, these abstract column vectors, are very closely connected to the kind of geometrical vectors we've been talking about earlier. And we can easily make a correspondence between the two ideas by establishing first a basis for our affine space. So if you choose vectors e1 and e2, then you can say, aha, this column vector A, which is 2, 3, can be interpreted by me as representing 2 times e1 plus 3 times e2. And you would picture that by going 2 times e1 plus 3 times e2 and adding those two vectors, getting the vector A. So you would say, aha, this vector 2, 3 actually represents this vector in my system. But somebody else could have a completely different frame of reference and may be thinking of everything in terms of vectors f1 and f2, say. That person would look at the vector a, 2, 3 and say, ah, that vector represents 2 times f1 plus 3 times f2, which is this vector A. So this person would have a different mental representation of what this abstract column vector means than this person. It's just a different point of view. So when we work with these abstract column vectors, somehow we're transcending any particular geometrical interpretation. Now let's have a look at the more subtle issue of matrices. So although we originally talked about matrices as being a bookkeeping device to keep track of a change of coordinates, it's possible and perhaps preferable to think of matrices as abstract objects independent of any particular application. From this point of view, what a matrix is simply an array of numbers. We're sticking to the two-dimensional case. Later on we'll talk about higher dimensions, but for now a matrix is just an array of 4 numbers arranged in a little square. And very convenient notation that helps us be a little bit general is this one here, where we talk about the entries of this matrix with indices. Okay, it's a little bit more complicated than using A, B, C, D, but somehow it keeps the bookkeeping a little bit more coherent and consistent. So here's the matrix A. We'll generally use capital letters for matrices, and whose entries are A11, A12, A21, A22. And we talk about the rows of this matrix. We talk about the columns of this matrix. So we could say that this entry here is the entry in the first row, measuring from the top down, and the second column measuring from left to right. That's why it has a 1, 2 there. It's in the first row and second column. While this one is in the second row, first column. Here's another matrix. Its name is B. It has entries B11, B12, B21, and B22. And here's our special matrix, the zero matrix, whose entries are all 0. What can we do with matrices? Well, first of all, we can do the same kinds of operations that we can do with vectors. Namely, we can scalar multiply, we can add and subtract, and we just do this component-wise. It's the most simple-minded thing you can imagine. So lambda times the matrix A is just what you get when you multiply each of the terms by lambda. That's called scalar multiplication because lambda is a number or a scalar. Here's how you add 2 matrices or subtract 2 matrices. So this matrix plus this matrix is what you get by definition when you just add the corresponding components. So you add these two, you add these two, you add these two, you add these two, and put them in the right places. To take the difference, A minus B, you would take this minus this, this minus this, this minus this, this minus this. That defines addition and subtraction of matrices. And now, the same laws are satisfied. Exactly the same laws that we wrote down for vectors are satisfied for matrices with respect to these operations. But what's interesting about matrices is that there's another operation, a much more interesting operation that you can do. It's the one we've already talked about. That's matrix multiplication. And that's really the source of the real interest in matrices, is that there's this non-obvious, beautiful multiplication defined on them. First of all, let's define the product of a matrix times a column vector. If there's a matrix here and a column vector to its right, then we define the product of those 2 objects to be this object, which is also a column vector. Although there's a bit of stuff here, this is all one entry. This is all one entry, so this thing only has 2 entries. And what is this product? This entry is the result of taking this entry of the matrix times this element of the vector plus this entry of the matrix times this entry of the vector. This times this plus this times this, that's what appears in the first entry. And in the second entry, what appears is the second row of the matrix times the column, this times this plus this times this. So that's the same multiplication we've already talked about. The product of a matrix times a vector. And our notation is just, there's the matrix, there's the vector, this is the product A times X. And now let's talk about the product of 2 matrices. There's the matrix A, there's the matrix B. This is the product matrix. It's also a 2 by 2 matrix. And it's very important to understand exactly how we get this product matrix. Okay. The simplest way to think about it, I think, is to think of it as being a repeated application of this simpler matrix times vector multiplication. What we're doing is best described in terms of columns. So let me describe how you get the first column of this product. The first column is the result of taking this matrix times this first column here, in that sense. So it's this times this plus this times this over this times this plus this times this. So the first column there is obtained by taking that matrix times the first column. And the second column is obtained by taking, again, this whole matrix times the second column. This times this plus this times this, this times this plus this times this. And this agrees with what we did earlier, and it guarantees that this fundamental equation is satisfied. That if we start with the vector x and we multiply by, say, b first, exactly in this kind of way, and then we multiply that vector by a, that's exactly the same as if we had started by multiplying the vector x by this composite matrix AB. So this equation is really defining the matrix multiplication for us, and this is the actual explicit formula that is required to make this work. All right, it's a very important formula. We're going to see it a lot. You're going to have to become very familiar with actually working the product of matrices using this formula. So let's look at some examples. A matrix times a column vector. What do? 2 times 5 plus minus 1 times 2. That's 10 minus 2. That's 8. Then 4 times 5 plus 3 times 2. 20 plus 6. That's 26. The product of this matrix times this column vector is another column vector. In notation, A times x equals y. That would be x, that would be y. Here's another example. Suppose we take this output, which is y, and multiply it by this matrix. Let's call it B. Minus 1, 1, 3, minus 1 times 8, 26. First entry is minus 8, this times this, plus 26, this times this. That's 18. Second entry, 3 times 8 plus minus 1 times 26. It's 24 minus 26. For the vector 18 minus 2. And now let's take a look at the product of two matrices. Let's take that matrix which we called A and this matrix B, and let's multiply them in this order. The order in which you multiply matrices is important. If we do it in this order, what do we get? So I want you to think in terms of columns first, okay? So we're going to multiply this matrix by this column first. So minus 2 plus 4 and 6 minus 4. That's the first column, which is 2, 2. And the second column, we take the second column here and multiply it. So minus 1 times minus 1, that's 1 plus 3, and minus 3 plus minus 3, which is a total of 4 minus 6. So when I'm actually working it out, I would work out this column first, and then I would work out the second column. That's the product of these two matrices, that's BA. And now let's check that if we take this matrix BA and multiply it by the original vector which we called x, then we're going to get the same thing as this thing here. This product is 10 plus 8 is 18. 10 minus 12 is minus 2. So here we got it as B times AX. There's AX. And here we got it as first multiplying B times A times X. Two are the same. For our last topic today, let's talk about determinants and a very important and beautiful theorem. The determinant of a matrix A, B, C, D is a number. And it's a number that we've seen many times. It's the number AD minus BC. That's the formula for the determinant of a 2 by 2 matrix. Later on, we're going to think about 3 by 3 matrices and higher. But for now, we're sticking with the 2 by 2 case. This is only one of several possible notations. Often we write determinant of A, just DET. And sometimes we write just absolute value of A. All those three mean just the determinant of A, that's the number AD minus BC. And here's our first theorem. Theorem is a major, important fact, which is usually not entirely obvious. It's that the determinant and this product of matrices are intimately connected. The determinant of the product of the matrices A and B is the determinant of A times the determinant of B. So A and B are matrices. This is another matrix. This is the determinant of that matrix. This is a number. This is a number. That's the ordinary product of numbers. Your first exercise to end this lesson is to prove this. To start with the matrix A, written out generally, start with the matrix B, written out generally, write out this product, calculate its determinant, then calculate the right-hand side, show that those two sides are equal. Very important exercise. Exercise 5.2 is to verify this formula in some special cases. You can pick any two matrices that you like, but you can start with these. So here are two matrices. Calculate both sides of this formula and verify that they are the same. Exercise 5.3, going back to our change of coordinates. I want you to invert this change of coordinates to find x1 and x2 in terms of y1 and y2. And then I want you to do the same with this one. A little twist that there's a rational number 7 over 2 as one of the coefficients. Our coefficients don't always have to be integers. The next exercise is to apply what we've done about systems of linear equations. You have two linear equations and you want to solve them. So here's one system for x and y, solve it. Here's another system for x and y, solve that as well. And the final exercise, a little bit of practice with matrix multiplication, which you're going to have to get very good at. Okay? So here are three matrices, A, B, and C, and I ask you to find A, B times C. So this means first calculate A times B, and then multiply it by C. And you have to make sure you do it in the right order, that C is on the right-hand side. And also A times BC. These two things should be the same. So it's a check for you to see if your arithmetic is good. And also CB times A and C times BA. These should also be the same. But these don't necessarily have to be the same as those. You can practice more matrix arithmetic by choosing any three matrices that you like and computing this kind of product for those three matrices. And they should always be the same. It's a check to see if your arithmetic and your understanding of matrix multiplication is right on. All right, we've covered a lot of territory in this lecture. Well done if you've been following and working hard. We are going to continue with 2x2 matrices. Eventually we're going to go on to higher dimensions, but there's a lot to be said just in the 2x2 case. Most courses in linear algebra do not spend enough time on the 2x2 case, in my opinion. Here we're going to have a really good understanding of this fundamental situation, which is in fact incredibly rich. So I hope you'll join me for that next time. I'm Wildberger. Thanks for listening.